Okay, now let's talk about covariance. Covariance measures the linear association between two variables. It is interpreted in a positive or negative value. So if it's a positive value that you get, you know there is a positive relationship. They move directly together. If there is a negative value, it means a negative relationship. They move indirectly, inversely. Now, the formulas are going to depend on whether you're looking at a sample covariance or a population covariance. Okay? And similar to the way we had sample standard deviations versus population standard deviations, the difference lies in the denominator. If you're looking at a sample covariance, you take the number of elements in your sample and subtract 1. If you're looking at a population covariance, you simply look at the number of elements in that population. Okay, let's do an example here. Say I have the following sample data on stock returns over 5 days for 2 different companies, ABC Corporation and their returns each day, and XYZ Corporation and their returns for each day. These are percentage returns, but they're in-whole numbers. So 1.1 means 1.1%, 2.1 means 2.1%, etc. First thing I want to do is identify what variable I'm going to consider my X and what variable I'm going to consider my Y. It doesn't matter which one you choose because we're looking at the covariance between these, but it is important to label them so that you don't make errors in your computations. Once you do that, X, Y, labels, you then will calculate the average for your X variable and your Y variable. So let's go ahead and put that in here now. Let's put average here and use the Excel function to find average. Scroll over the data and click return. And there's our average return over the 5 days for ABC Corporation. We pull this box over. There's our average return over the 5 days for XYZ Corporation. All right. Now that we've done that, we can then start to do our computations. Now we're dealing with a sample here, so we're going to use this formula. It looks like we need to find the difference between each X data point and its mean. So let's do that here. Put equals each X value minus the mean that we just calculated. And remember, we're going to have to lock this cell because when we drag down the boxes, we want that to stay static. So we're going to drag this down. And now we have our X minus X bar. For example, this one here, 0.2 minus 1.3. Or this one here, 2.1 minus 1.3, so on and so forth. Now let's do the same thing for the Y's. I'm going to move this formula over slightly so we can see the Excel box and still see the formula. Okay. So what we're going to do here is take our Y value and subtract it from our mean for Y, which is right there. And again, I'm going to need to lock that because I want to be able to pull down the boxes. Okay. And then drag this down. And there we go. Now you'll notice here I have 3 minus 3.74. Here I have 4.9 minus 3.74, so on and so forth. So I've essentially calculated this and this. Now I need to multiply them together. So that's going to be my next column. This times this. And I don't need to lock anything here because I actually want to drag down the formulas. I want this times this, and I want this times this, so on and so forth. So now I've got everything up to summing. So let's go ahead and sum those. Equals sum. Okay. And we'll just scroll over our data points here. We get 2.66. So that's our numerator. And then we take that and we divide it by n minus 1. Well, we have 5 days. minus 1 is 4. 4. And you get 0.665. So our covariance, okay, done manually, is 2.6 or 0.665. Okay. And now we're going to take the easier route and do the covariance with Excel. And you're going to like this because you just click on put equal covariance, and we want to sample, so .s, not .p. Okay. And we're going to pull up the window, and our array, our first array, is going to be our x values, and our second array is going to be our y values, and bam, you get the exact same thing. So 2 routes to the same end. Using Excel is easier, but it's good to practice the manual one so that we learn the process that Excel is taking to get us those numbers. Now let's move on to the correlation coefficient. This is related to the covariance in that it measures the strength of the relationship between the two variables. So the covariance tells us if there is a relationship, positive or negative. And the correlation coefficient tells us how strong that relationship is. To calculate the correlation coefficient for a sample, we use this formula here. And for a population, we use this formula here. Okay? The numerator is the covariance that we just calculated, and the denominator is the standard deviation of our x values times the standard deviation of our y values. Okay? So in essence, it's taking the covariance that we already calculated it and dividing it by the standard deviations of the two variables. Okay? If it's a population, it's the same thing. It's the covariance of the two variables divided by the population standard deviation of x and the population standard deviation of y. So essentially the same formulas. All right, let's go ahead and look at some data here. Using the same information we just calculated for the covariance, we can calculate the correlation coefficient. Okay? And we can do this manually, and then we can do it using an Excel function. Okay? Let's go ahead and do it manually first. So what we're going to do is first find the correlation, the covariance for x and y. And we already did that, right? So we can put equals covariance, which we know is 0.665, but we're going to divide that by the multiple of the standard deviation of our x variable times the standard deviation of our y variable. We don't have that yet, so we need to go ahead and get that. So let's put over here the standard deviation and do the calculation. Okay, so equals, we've done this before, standard deviation of a sample. Okay, and we want to scroll over our returns for x, and then the same thing for y, right? Scroll over the returns. Okay. And we can go ahead and round those if we want. We'll leave them. The computation now is easier because we can put equals our correlation or covariance, and we can divide that by the standard deviation of x times the standard deviation of y. Okay. You get 0.95425. Okay. Now, if we use Excel for our correlation coefficient, we simply find the function correl, okay, and let's pull up the arrays. So we're going to have our x values for the first array and our y values for the next array. Click OK. And that did not work because I did not correctly scroll over the second array. It's right there. And click OK. And you get the exact same value. Okay. So manually or Excel. that's now open for interpretation because we already know from the covariance that there is a positive relationship because it's a positive value. So returns for X go up, returns for Y go up. However, now we have more information because we can see the strength of that relationship. And the strength is pretty high because remember, it says here, when you get close to +1, you have a strong positive relationship. And we have 0.954. So we're very close to 1. So not only is there a positive relationship that the covariance tells us, but it's a strong positive relationship that the correlation coefficient tells us. Okay, so very good information. A lot of these tools are used in finance because, again, you might want to determine what the relationship is between different assets or different commodities, things like that. Okay, now let's do some practice. First question says, using the body fat practice data set, find the range, interquartile range, standard deviation, and variance for height. So here's the data set, and the first thing we want to calculate is the range for height. We're going to scroll over our data, and we're going to go up here to data and sort, and we just want to sort by height, smallest to largest. And now you've got all your data. Remember to scroll over all your data so that it keeps everything intact. Once you have it sorted, you can just look at the high and the low. So we have a high height of 76 and a low height of 29.5. So we could put range here and put equals the high, 76 inches, minus the low, 29.5, we have 46.5. Now another way to do this is the data analysis tool pack. Go here, go to descriptive statistics, and then scroll over your height. Labels in the first row, okay, because we do have it labeled. Output, let's put it right here, and summary statistics. Click OK. And you're going to get a lot of stuff here that may be usable later on, but notice the range. We have the same value, 46.5. Okay, so either way will get you the range. The next piece of data we want to collect is the interquartile range. And for that, we're going to use the quartile function. We're actually going to create our first quartile, our second quartile, and our third quartile. Okay? And recall that for the quartile function, pull it up here, quartile. Okay. And let's go ahead and pull up the function itself. Our array is going to be height. Okay. So we're going to click on that, and we want the first quartile initially. Okay. And then we can drag this down and just change the quartile numbers. So here we want the second quartile, and then here we want the third quartile. Okay. And remember, when you use the quartile function, it actually gives you the values, in this case height, that pertain to those demarcations, right? And so quartile 1 is 67.81, quartile 3 is 72.06. So we can find the interquartile range by taking the third quartile, okay, so we'll put equals the third quartile minus the first quartile, okay, and you get 4.25. Remember, the interquartile range is effectively chopping off any data below the first quartile, so anything below this number, and anything above the third quartile. Okay? It's looking at that portion between these two. So anything above 67.81 and below 72.06. So that range of values is 4.25. There is a height range that is around 4 inches. Okay, so we'll pick up with this in the next video. Thanks.